Okay, so this is section 1.5 of the textbook. This section is on limits. Okay, the limit of a function. So let's suppose that suppose f is a function, and this will be defined near the number, let's call it a, near the number a, not necessarily at a. Okay, it doesn't have to be defined at the number a, but it has to be defined near the number a. Then we say the limit of f of x as x approaches a is equal to L. So this is the limit of f of x as x approaches a is equal to L. That's what we say, and we write this math symbol. Excuse me if you hear noises outside. I have my windows open because it's a gorgeous day, and there might be some traffic you'll hear in the background. Anyway, so we say the limit of f of x as x approaches a is equal to L, and we write this limit equals L if, so this is if we can do the following. If we can make the values of f of x as close to L as we like. As close to L as we like by taking x values very close to a. Very close to, but not equal. Remember, we did not assume that f was defined at a, so we have to say but not equal to a. Okay, so this is the definition of a limit. Now, the limit is a very intuitive notion. The math definition looks a little intimidating, but really it can be boiled down to a geometric condition on the graph of a function. On the graph of y equals f of x. So here's how that goes. So I'm just going to draw. I'm going to draw a pair of axes here, and I'm going to indicate the number a, and I'm just going to, I just want to block out this coordinate. Okay. And I really want to block it out, so I'll block it out in just a minute. But I'm going to draw a function that I'm just going to make up. Okay. So here is a function. There it goes. Okay, and this coordinate right here is the number L. Okay, so I'm literally blocking out what's going on right at the x value of a. Okay, so what the notion of a limit says is that if you're looking at the behavior of the function, the trend that you should see in terms of the height value of that function, in terms of the value that function takes, is that if you're very close to being near a on the x-axis, then the points on the graph should be very close to being at height L. Okay, so here in this case we would say exactly this, that the limit, so this is f, the limit of f of x as x approaches a, and we use this little arrow symbol, x approaches a, is L. Okay. That's really all there is to it. Now, why do we say things like trends? Okay, so an example why this the trend is important is because you aren't always able to plug in. You aren't always able to plug in. So this is this is approximately what the graph of the function sine of x over x looks like. It looks a little bit like sine, but not quite. So it goes something like this, and then it's symmetric, so it should look something like this. Okay. This is approximately what the graph of sine of x looks like if you were to plug this into your calculator. Okay. So what do you notice here? Well, the first thing to notice is that, oh well, if we're at the x value of 0, the limit as x approaches 0 of this function sine of x over x, it appears to us to be 1, right? If we're just looking at the trend of this function as we approach 0 on the x-axis, the function seems to be wanting to pass through the height of 1 on the graph. Okay, so this is the first observation we make. The second observation we make, however, is that sine of 0 over 0 is not defined. Okay, so you can't just plug 0 into this. So if you took your calculator and tried to plug 0 into this function, you'd get an error because you can't divide by 0, of course. That does all kinds of damage to the universe. So this is really why we make that stipulation before, is that limits only, we only need limits. Excuse my cat. We only need our function to be defined near when x is equal to 0, and not at x equals 0, and not at x equals 0 in order to discuss limits. Okay, good. So we can talk about one-sided limits as well. So the notation for this is the limit as x approaches a from the positive side of a, or from the right, and x approaches a from the negative side, or from the left. So this is from the right, and this is from the left. Okay. An example of a function that I might draw here is something like this. So here's the graph of f. Notice it has a jump right here. Let's make this value here equal to m. This particular height value will make it m, and this particular height value will make it L. And so the same question as before. So let's take a look. From the right-hand side, maybe we'll mark this. Here's A. Okay. From the right-hand side, from the right, that notation, notice the A plus, so we're coming from the positive side of A. The trend of the function seems to be that it wants to hit height L. Okay. You can certainly see that if I cover up this graph, this coordinate at x equals A with the pen. The trend seems to be that it wants to hit height L. And from the other side, from the left, the trend seems to be that it wants to hit height M. All right. And so these are one-sided limits. In this case, so since L does not equal to M, the two-sided limit doesn't exist. Does not exist. DNE stands for does not exist. So we would, in fact, that's a necessary condition for the limit to exist, is that the two-sided limits must exist and be equal to each other. one-sided limits. Okay. One other kind of limit we might consider, infinite limits. So here's an example. How about the limit as x goes to 0 of the function 1 over x squared. So what could that be? Well, here's what the graph of this function looks like approximately. I'll do my best to draw it. It should look somewhat even, the graph of this. Obviously, this is not defined as 0. You cannot plug 0 in here, and so we're really asking about the trending behavior here. So the graph as x becomes very, very large, but with a negative sign, 1 over that squared goes to 0. So this graph will have what we call a horizontal asymptote at the x-axis. Horizontal asymptote. Horizontal asymptote is y equals 0. It goes to 0 in both directions in height. Now, what's the trend as we approach to 0? Okay. So again, I'm going to cover this up. And well, what's happening? If we come from the negative side of 0, it seems like the function is going to just climb forever without any sort of bound. And if we come from the positive side of 0, it does exactly the same thing. So in this case, we say that the limit is infinite. And we say, we either write this, or you can say it does not exist. I mean, infinity doesn't technically exist. These are both correct answers to this question, but the trend is what's most important. Being able to observe that the graph of this function from either side of 0 is shooting up without any sort of bound. One more example along these lines. About 1 over x minus 2. So here's our function. Let's just take a look at this graph and then ask ourselves what kinds of limits might make sense for this. So clearly this function is not defined at 2. Let us mark that. And when we are on this side of 2, the graph looks to me like it should be negative, and when we're on this side, it looks to me like it should be positive. So we might see some sort of behavior of this function that looks like this. All right. Well, if you graph this, this will look approximately like what the function will look like on your calculator. So let's analyze this just a little bit. What kind of limits, what kind of trending behavior might we ask ourselves going on here? Well, it doesn't seem to me that there's a consistent trend from one side or the other, but it does seem as though there's a trend of going downwards without bound from the left side of 2 and going upwards without bound from the right side of 2. And in fact, that's the case. The limit as x goes to 2 from the right-hand side of 1 over x minus 2 is equal to plus infinity. We could also say it does not exist. And the limit as x approaches 2 from the left-hand side is equal to minus infinity. Also does not exist. Now, because of this, therefore, you'll remember the 3 dot symbol means therefore. The limit of this function as x goes to 2, this does not exist. Okay. The reason it does not exist is because there's not an agreement of the trends at these. Very good. That's the end of section 1.1.